Here are the problems on the wave nature of light. It says problem set number 11. It includes problems from interference, diffraction, and polarization. So there are 15 questions, and this is really important for the exam. Talks about chapter. Okay, no. The first problem talks about monochromatic light falling on two very narrow slits, 0.048 millimeter apart, and successive fringes on a screen 6 meters away are 8.5 centimeter apart near the center of this pattern. Find the wavelength and frequency of the light. So this is about Young's double slit, and you have the two slits here showing up. The distance between the two slits is the D here. L is the distance between the slits and the screen, and both of these are given. You have small d there, distance between the slits. You have the distance from the slits to the screen. But this in here is actually the distance between successive bands or successive fringes. And it's monochromatic light, so it's single wavelength. And we know that for small angles, sine theta, now understand that this distance from the center of the screen to a certain point is x. And for small angles, we can actually take sine theta as x divided by L. Really, it should be tan theta, but when theta is small, sine theta is equal to tan theta. And the path difference is d sine theta. You know that. The path difference here is d sine theta. And the condition for brightness is that it should be equal to m lambda. Condition for brightness. So substituting and making x the subject, you get x is equal to lambda m times L by d. So x1 would be lambda m1 L by d, and x2 would be lambda m plus 1 L by d, because the question talks about successive fringes. So if you take m as the number of one of the bright bands, then the next one is m plus 1, isn't it? Because it's the next one, right? It could have been m minus 1. It's not going to make a difference. But now if you take the difference between them, x2 minus x1, you get lambda L by d, and make lambda the subject. You get d delta x by L. And you have all the terms now, because what's given as 8.5 centimeter is actually delta x. So you have all these three quantities, plug them in. 4.8 times 10 to the negative 5, that's in meters, times 0.085 by 6, and you will get 6.8 times 10 to the negative 7 meter. That's the wavelength. To find the frequency, you know that frequency is the speed divided by the wavelength. Speed of electromagnetic waves is 3 times 10 to the 8. So when you divide that, you get 4.4 times 10 to the 14 hertz. In this question, you have light of wavelength 680 nanometers producing fringes on a screen 2.6 meters away, and the third order fringe is 38 millimeter. 38, so that's x. What is the separation of the two slits? You have to find small d. Direct question, let's assume that it's talking about bright bands or bright fringes. And we know that for brightness, the condition is d sine theta is equal to m lambda. Now, as explained before, for small angles, sine theta is approximately equal to tan theta, which is x by L, and put them together. So you have d is lambda ml by x, and lambda is in nanometers, which should be 680 times 10 to the negative 9. M is 3, L is 2.6, and x is 38 millimeter, which is 38 times 10 to the negative 3 meter. On a calculation, you get 1.4 times 10 to the negative 4 meter. In this question, it's a double slit experiment. It's found that blue light of wavelength 480 nanometer gives a second order maximum at a certain location on the screen. So x is not given. Now, what wavelength of visible light would have a minimum at the same location? So now you see that in this question, it's kind of comparison, because x is the same, the distance between the slits is the same, the distance from the slits to the screen is also the same. And there are two conditions that you're comparing. One talks about maximum being produced at a certain location, and then it says, where would you have, what wavelength would produce a minimum at the same location? So for maximum, the condition is path difference d sine theta equal to m lambda. It says, let me slow this down, it says that the second order and wavelength is 480 times 10 to the negative 9. So that gives so many meters. And for minimum, the condition is d sine theta should be equal to m plus half a lambda. And here we're saying the wavelength of visible light would have a minimum. Okay, so because d sine theta is the same, because the left-hand side has to be the same. Why? Because it's saying it has to be produced at the same location. So x is the same, which means d sine theta is the same. And that's why I have put the right-hand sides equal to each other. See, this is equal to this, okay? And then I could find the value of lambda. Assuming that m is 1, then you would get 3 by 2 lambda, because you would have 1 plus half, which is 3 by 2. And then lambda would be 640 times 10 to the negative 9 meter. And this wavelength is in the visible region. So that means that's the wavelength that would produce a minimum at the same location. In this question, it's a double slit experiment again. The third order maximum for light of wavelength 500 nanometer is located 12 millimeters from the central bright spot on a screen 1.6 meter from the slits. So you have the wavelength, you have x, and you also have L. Light of wavelength 650 nanometers, so that's the second wavelength, is then projected through the same slits. How far from the central bright spot will the second order maximum of this light be located? This again is a comparison problem. You have two wavelengths and you have some constants here. The distance between the slits and the distance from the slits to the screen, that doesn't change. And you're looking for the new value of x, because it says how far from the central bright spot. Okay? And both are talking about maximas, right? And in the last problem, we proved that d is lambda ml by x. I'm just using that from one of the last problems. Okay, so from there, x is, because you're looking for x, let's make x the subject. And then set it up as a ratio. x1 by x2. All right, when you divide, you take the reciprocal and multiply, right? That's why it's reversed, and these factors get cancelled out. And this time you can keep it in nanometers because both lambda 1 and lambda 2 are going to be in nanometers, right? And then you have M1 is 3 and M2 is 2 because that's what the problem says. And therefore you get X2 is X1 by 1.154, which is 12 millimeter divided by 1.14, and the answer is 10.4 millimeter. This question is to do with thin films. You see that when a thin piece of plastic, refractive index 1.6, covers one slit of a double slit apparatus illuminated by 680 nanometers, the center point on the screen, instead of being a maximum, is dark. What is the minimum thickness of the plastic? Now, the introduction of the thin plastic into one of the beams changed it from being a maximum to a minimum. This means that the extra path difference created by putting that thin piece of plastic should be lambda by 2. Why? Because for a maximum to change into a minimum, there should be a shift of half a wavelength. It should have gone from a crest to a trough. Now that's a very crucial point to understand, because maxima and a maxima produces brightness. It's a maxima and a minima that produces darkness. So if we take the number of waves in the plastic minus the number of waves that travel through air, because initially the wave was completely traveling through air. Now you have a small thin plastic, so a certain number of waves is traveling through the plastic. The difference must be equal to half, right? And how do you get this? Because number of waves is just thickness divided by wavelength. Thickness divided by wavelength. For example, if the thickness is 1 meter, that's just a wild example. If the thickness is 1 meter and the wavelength is 10 centimeters, you're going to have 10 waves. 1 meter, that's 100 centimeter divided by 10 would be 10 waves, right? So that's the reasoning here. So for air, you have T minus lambda. And for plastic, you have T by lambda P. What's lambda P? The wavelength in plastic. And lambda is the wavelength in air. Now I got to find a relation between them. The ratio of the wavelengths must be equal to the refractive index. That is from the definition of refractive index, which gives lambda P is lambda by n. So now we can substitute and get both in terms of lambda. See, what I've done here is I've substituted for lambda P right there. Substituted for lambda P, and you get nt by lambda. Now I can take out t by lambda as common, so it leaves me with the n minus 1, and this must be equal to half. Now where do I get this half from? That is what I was trying to explain in the beginning, that the shift must be equal to half a wave. Or say, because a crest became a trough, it's a half a wave. So that's how I get that half from. Now make T the subject, because you're trying to find the thickness of the plastic. Rearrange it, and lambda is in nanometers, so 680 times 10 to the negative 9. You put all that down, you get 570 times 10 to the negative 9 meter. Now this problem is to do with thin films again, and you know, depending on the thickness of coating on a lens, it can appear differently colored. This is one way how people have different colors for their contact lenses. You know, trying to look beautiful, trying to have bright colored eyes. This is what they do. So this question talks about a lens appearing greenish yellow when white light is reflected from it. What minimum thickness of the coating do you need? The refractive index of glass is also given. All right, directly, let's draw this diagram. See, so what happens here is the incident ray is reflected and partly refracted. And the refracted part is again reflected and then refracted back. So you see that this is traveling through Now, another thing that you have to understand here, and that's very important, is this reflection is taking place when the light is trying to go from less dense to more dense. Therefore, there will be an additional path jump of lambda by 2. Now this is the coating, and its refractive index is, how much is that? It's 1.25. And this is 1.52, that's the glass. So you have the second reflection also taking place, this reflection, also taking place when light tries to go from less dense to more dense. So that additional path jump of lambda by 2 takes place in both reflections 1 and 2. But this ray additionally travels this distance here, which is about 2 times the thickness of the coating, because this is the thickness of the coating. This is like 2 times the thickness of the coating. Therefore, this path difference should be 2 times the thickness of the coating. And that's a mistake. That should be multiplied by the refractive index plus lambda by 2. Okay, I'm going to correct that. And the reason why you need that here is because it's moving through a material. You need to multiply it with the refractive index of the material, because this ray is only traveling through air. So you got to multiply this with the refractive index of the material. So the path difference is going to be the actual difference between these two. And I'm still writing the wrong thing. It should be 2nt. I'll correct it. So path difference is actually this minus this. So the lambda by 2's will get cancelled. And for constructive interference, we know the path difference must be equal to m lambda. So with minimum thickness, for constructive interference with minimum thickness, delta is equal to lambda. How do I get that? Because m is 1. Remember, the condition for maxima is m lambda. I'm just taking m as 1. Okay, now I've corrected it. Therefore, now rearrange and make t the subject. You get lambda by 2n. Lambda is given as 570 times 10 to the negative 9 because it's in nanometers. And refractive index is 1.25. That's of the coating there. You calculate it, you get it as 228 times 10 to the negative 9 meter. And I'm trying to stress this point that when reflection takes place at a denser surface, that means when it's trying to go from less dense to more dense, like in both these cases, there will be an additional path jump of lambda by 2. And also, since it's moving through a material, you will have to get the path difference, you have to actually take the geometrical path difference, which is 2t and multiply it with the refractive index of the material. Hope that makes sense. The seventh question, a thin oil slick floats on water. A beam of white light strikes this film at normal incidence from air. The only enhanced reflected colors are red and violet. From this information, deduce the minimum thickness of the oil slick. Again, to do with thin films, you have the oil and then you have the water there. And okay, so you have light partly reflected, then again, like in the last case. But you see, you're going to see a difference here. The first one takes place when it's trying to go from air into oil. So obviously that reflection takes place when it is going from less to more dense. But this reflection takes place when it's going from oil into water. And that is, oil has a higher refractive index and water less. So that reflection takes place when it's going from more dense to less dense. What does that mean? That means there is no additional path of lambda by 2 here, but there is here. Okay, so there is an additional path lambda by 2. I'm trying to list the refractive index of each one. Let that thickness be t. Geometrically, the path difference is 2t, but you've got to multiply it with the refractive index, right? And now you see that this is equal to 2nt minus lambda by 2. Why? Because the second one, there is no additional jump. Set that equal to m lambda. That's the condition for brightness, because it says the enhanced means brightness for constructive interference. Rearrange that. Take lambda by 2 to the other side. Take out lambda, and then make t the subject. And substitute. If you substitute lambda as 650, you will get the thickness as 108. How do I get 3 values? Because I'm giving m values 1, 2, and 3. So when you give it 1, you get this. When you give it 2, that's the value. When you give it 3, that's what you get, all right? For the other wavelength, let's do the same. When it is 390 nanometers, you're going to get 3 results: 65, 195, and 325. And when you compare them, you see that you have 325 for both. Therefore, the minimum thickness needs to be 325 nanometer. Why? To produce maximum in both these wavelengths. And the 8th one, how thick should the air layer be between 2 flat glass surfaces if the glass is to appear bright when 450 nanometer light is incident normally? What if the glass is to appear dark? So now you have 2 flat glass surfaces and you have air between them. That totally changes the situation. All right, that's the setup now. You got glass, air, and then you got glass. So the first reflection is trying to go from more dense to less dense, and the second one is trying to go from less dense to more dense. You see how the situation has changed? Therefore, when you take the path difference, the second one has an additional jump of lambda by 2, and now the path difference will be 2nt plus lambda by 2 because it's the second one that jumped by lambda by 2. And rearrange that, make t the subject, substitute the numbers. And take t is m is equal to 1. So you would get t minimum as 113 nanometer. And then the question has the second part. It says, what if the glass is to appear dark? So now you go and say the condition for darkness, which is 2m plus 1 lambda by 2. Now, that's the same as m plus half lambda. Look at it. 2m plus 1 lambda by 2 is the same as m plus 1 lambda. Rearrange that. Once again, make t the subject and calculate. I missed lambda. Okay, I put it there now. So you get 225 nanometers. So if you wanted it to be dark, it should be 225 nanometer.